Welcome to Power Electronics Education Electronic Book, Lecture 4, Control Rectifiers. This lecture is presented by Dr. FIRUZ ZARE. Now we change the firing angle in a three-phase full-wave rectifier, still with resistive load. So here we can see that increasing the firing angle into 45, still we have continuous voltage waveform. That means the voltage is not getting negative. In this case, the output current is positive. That means thyristor can conduct. So still we have same scenario, but when we increase the firing angle beyond 60 degrees, in this case, we can see that output voltage, because of having line voltage, for example, if we concentrate on this line voltage, here we can see that at this zero crossing point, line voltage is getting negative. So from this time till this time, that means over this period, because line voltage appears across the load, because over this time the output voltage is getting negative, and because current is voltage divided by resistor, so because this one is negative, so that means current should be negative. If current is negative, that means current through the thyristor should be negative. So in this case, thyristor is getting off. So here we can see that for some applications, if we increase the firing angle beyond 60 degrees, in this case, we may turn off the thyristor with resistive load, and we have different output voltage which should be calculated based on these limits. So the limits of integral are different for this case. So we can find the output voltage for a three-phase full-wave rectifier with resistive load when the output voltage is not continuous and the thyristor is turned off for a short period of time. So in this case, again, we can concentrate on this equation, which basically based on this equation. So the difference is that, as I mentioned before, because we change the time frame and we move the axis into this time, so because this interval is defined by quarter of cycle, so that's why this zero crossing point is t over 4. So the only difference is that we change the upper limit based on the previous equation into t over 4, and we need to basically find this integral. So in this case, again, the integral of cosine is sinus. We just put the upper limit and lower limit. So we can simplify into this equation, because basically when we put the upper limit, so sinus 2 pi t times of t over 4 can be simplified as sinus pi over 2, which is basically this term, and then the lower limit in this equation gives this term. So finally we can simplify, because sinus pi over 2 is 1, and if we multiply this term into this equation, in this term is pi over 6 times of minus, which is minus pi over 6 plus 2 pi delta t over t. So the output voltage can also be defined as firing angle, because delta t equals to t times of alpha divided by 2 pi. So if we put here, we get output voltage, which is equal to 3 root of 3 Vm over pi 1 plus sine s pi over 6 minus alpha. So now we can analyze a three-phase full wave rectifier with an inductive load. So basically similar to a resistive load, we have two sets of thyristors, upper group and lower group, in which the upper group provides positive voltage at this terminal and this group provides negative voltage at this terminal. And that means that we can have positive voltage based on this group of thyristors, which creates this voltage waveform at this terminal, and this set of thyristors generate this voltage basically at this terminal, and finally output voltage is this voltage minus that voltage. So that means a portion of line voltage appears across the load, and the point is that because output current is continuous, so at different firing angles we have continuous current. That means we have continuous voltage waveform. For example, if you look at another voltage waveform when the firing angle is 45, so in this case similar to a resistive load, because the output voltage is not getting negative, so still we have continuous voltage waveform. But at this firing angle, because the output voltage is getting negative, so here we have negative voltage, but because the output current is positive, so that means current through this thyristor, for example, is positive. So in this case that thyristor conducts. But the point is that when we turn on another thyristor, because the other phase is greater than that phase, so the voltage across this thyristor becomes negative. So that's why we turn off this thyristor once we turn on either this thyristor or that thyristor. That means natural commutation. So in this case, just because of inductive load, because current through the load is continuous, so in this case we may have negative voltage at different firing angles. In some applications, if we need to control the output voltage and just provide positive voltage, we can have a single phase full wave half control rectifier, which is basically for inductive load and operating at large firing angle. So in this case we have two sets of switches. The top one is, for example, thyristor, and the bottom one is diode. So in this case we can apply gate signal, for example, to this thyristor. So at this firing angle, when we apply gate signal to thyristor 1, T1 is turned on, and because the voltage across this thyristor is positive, so that's why D2 conducts. So at this zero crossing point, because the input voltage is getting negative, that means the input voltage can be defined as negative voltage with this polarity. So if you look at this diode, when this diode conducts, that means this terminal is negative, and because this diode conducts, this terminal is positive. So in this case this diode conducts, that means we turn off this diode and we just circulate the load current through this D1 and T1. So in this case we have T1 and D1 in on state, and if these two are on, that means the output voltage is 0 because there is a short circuit. So when we turn on D1 and T1, so the output voltage is 0. Suppose that the voltage drop across the diode and thyristor is 0. So the current basically circulate through this current loop, because assuming that the load current is continuous. So basically for this time interval, T1 and D1, they conduct, but when we apply gate signal at this firing angle into the second thyristor, so because the input voltage is negative, as we can define based on this polarity, so here if you look at the voltage across the second thyristor, because this terminal is basically negative and this terminal is basically positive, so we have positive voltage across the second thyristor. So once we apply gate signal into this thyristor, that means we can turn on the thyristor, and once we turn on the thyristor, because this point, this terminal is positive and this terminal is negative, so that's why the voltage across the thyristor is based on this polarity, which turns off. So in this case, over this cycle, T2 and D1, they conduct, and these switches are on, and we have this portion of input voltage with this polarity across the load. So here we can see that we have only positive voltage across the load, and we have also control, we can also control the output voltage by changing the firing angle. So these voltage and current waveforms just show the output voltage and current based on different firing angle. So here again we can see that we can change the output voltage because this area is changed by different firing angle, and again over this time we just turn on one thyristor and one diode in such a case that the output voltage is 0. That means we short circuit either through this line or this line for this period or this period, and here you can see that the output voltage is changed. Or when we increase the firing angle to this 105, again we can see that the output voltage is decreased. So basically this is for some applications when we need just positive voltage and we need to control the output voltage. We can analyze a three-phase full wave half control rectifier based on an inductive load. In this case the firing angle is 15 degrees. So basically we have two sets of switches. The first one consists of thyristors, which provides positive voltage, and that voltage is controlled because we can change the firing angle. The second set consists of diodes. In order to analyze this topology, we just concentrate on half wave control rectifier and half wave diode rectifier. That means these diodes generates negative voltage at this terminal. That means we have this voltage. Because we have diode rectifier, there is no control on this voltage. So here we can see that, for example, if one of the phase is lower than other phase, that diode conducts. For example, in this leg we have one thyristor, one diode. This thyristor is responsible for positive voltage of, for example, phase A, which means create positive voltage, or we can change the firing angle when phase A is greater than other phases. And this diode is generating negative voltage. That means when phase A is lower than other phases, that means D1 conduct. So in this case, for example, let's concentrate on this interval. On this interval, basically we apply gate signal in this thyristor T1. So T1 is turned on. So we have this portion of phase A. So here is phase A. And this terminal is basically connected to phase B because phase B is lower than phase C and phase A. So that's why the output voltage over this time is line voltage, which is basically VAB. Now over this cycle, here we can see that phase C is lower than phase B and phase A. So in this case, this diode conducts. That means this terminal is connected to phase C. And because still phase A conducts, so that's why we have phase A until this time that we're going to apply gate signal to this thyristor. So that's why over this cycle, here we can see that we have line voltage, which is basically this line voltage, VAC. So line voltage appears across the load over this cycle, this time, whereas in the previous time we had VAB. So over this cycle here we can see that T2 is turned on. So this portion of input voltage appears at this terminal. That means phase B is connected to this terminal, whereas this terminal is connected to phase C. So over this period, the output voltage is VBC, line voltage of BC, and just at this point, because phase A is lower than phase C, so that's why beyond this time this diode should conduct, and the reason is that phase A is lower than phase C. So again for this cycle, because still phase B is connected to that terminal, that means T2 is on. So here we have phase B, and because over that cycle phase A is lower than phase C, so that's why this diode conducts. So in this case phase A is connected to this terminal. So what's happened here, we have this line voltage across the load. That means over that cycle we have phase B minus phase A, which is this line voltage. So over that cycle we can see that we have another line voltage. That means we can basically get different voltage waveform by controlling the firing angle of this set of thyristor, whereas this set of diode cannot control that terminal's voltage. So finally over this period we apply gate signal to third thyristor, and the reason is that phase C is greater than phase B and phase A. So that's why once we apply gate signal, this terminal, which is phase C, is connected to this terminal. So that's why this terminal has this voltage. And over that cycle here we can see that still phase A is lower than phase B and phase C. So that's why this diode conducts. That means this terminal, which is phase A, is connected to this terminal. So here we have this line voltage, which is basically VCA. So when we change the firing angle, then we have almost same voltage waveform. So at this firing angle, which is less than 60 degrees, in this case we have almost same voltage waveform. That means line voltage appears across the load. But the point is that because output voltage is not negative, so still we have same scenario. But when we increase the firing angle to 75, in this case there is different case. That means let's concentrate on this interval For example, phase C is lower than other phases. So in this case, this diode conducts. So because load current is continuous, so that's why we have load current through this system. So in this case, because we turn on T1, so from the top group, this thyristor is turned on. So this is the current loop through the supply. So now, because the line voltage is getting negative, that means here, because phase C is not lower than other phases, so in this case phase A is lower than other phases. So what's happened here, if you look at this terminal, because this phase conduct, that means phase A minus phase C in this case is negative. So if it's negative, that means this diode can conduct, and once this diode conduct, this one is off. So if this diode conduct, that means we have short circuit across the load. So this diode is off, that means the current circulates through this line. There is no current through this line, and if we look at the load current, can be circulate through T1 and D1. So we can actually redraw the current loop. So here current pass through D1 because we turn on D1. T1 already was on, so that's why we circulate the current over this cycle. So in this case, instead of having negative voltage, which can decrease the average voltage, we just short circuit the output voltage. And in this case, we can also control the output voltage by changing the firing angle, but we have no negative voltage across the load.